Yeah, so question 4 is a bit odd question. It's a bit of Doppler effect, a bit of redshift, and a little bit of nebula and main sequence stars. So figure 6 shows two objects, E and D, and we can see those on that line. E's emitting a sound, so I'm just going to make a little note. Okay, so you're emitting a sound out. D detects the sound. E is moving, shown by the arrow, so E is moving away. E emits a wavelength, so the lambda equals, that lambda side's a bit pants, lambda equals 1.86. D measures the wavelength as 1.98. Okay, so we can see this is making 1.86 and then D detects 1.98. So we know that's making 1.86 meters. This detects 1.98 and that's because it's moving away, so the wavelength has been stretched. Okay, so that makes sense. This is the Doppler effect. Just the same way as an ambulance approaching you, the pitch rises, and then as it moves away from you, you have the as it goes away. That's the waves being stretched. So it says, calculate the difference between the wavelength that E emits and what D detects. Well, that's easy. Take the two numbers away. 0.12 meters. So we now find out how much the wave's been stretched by the Doppler effect. The next one is we've got an equation that we've just got to use. It tells us to use this. The velocity of sound is 330 meters per second. We want to find the velocity of E. What's the speed of E? And it's the velocity of sound multiplied by the time difference multiplied by the wavelength of E. So we can just pull down our information. So speed of sound, 330, multiplied by the time difference. That's what we worked out in the question above. So that's what makes this quite tricky. All divided by E, the wavelength of E, which we said was 1.86. And now we've worked out the velocity is 21.3 meters per second. So it looks tricky. It's actually quite nice. Go on to the next part. The wavelength of light emitted from distant galaxies is different when light is detected on Earth. Explain the difference and how it shows that the universe is expanding. So imagine here's Earth, here's a galaxy, and it's whizzing away. We know that just like the previous example, the waves will get, so here's what it normally emits. But because it's moving away from us, this wave gets stretched, and we call that redshift. And this tells us that it's moving away. So now what's interesting is things that are further away are more redshifted because they're not just moving away, but they're moving away at a faster rate. So first part, the wavelength is increasing, or the waves have been redshifted. And this shows us that the galaxies are moving away from Earth. Next one, CMB radiation, so the cosmic microwave background radiation, provides evidence of the Big Bang, that we had a beginning. Use the table to find the wavelength of CMB. So really it's checking, did you know that the M is microwaves? There we go. So that's going to be 1 millimeter. During the evolution of a star, the nebula collapses and becomes a main sequence star. State what causes the nebula to collapse. So that's gravity. Then it says, explain why the nebula stops collapsing as it becomes a main sequence star. So, in a nutshell, we've got a collection of dust and gas. In one area, there's slightly more particles. Therefore, it's got more gravity. That pulls it in and it does work. So, force times distance, or gravity times distance. This work then increases the temperature and increases the pressure until we get nuclear fusion. When nuclear fusion takes place, we then end up with a period of a protostar where it's not stable, but eventually it becomes a main sequence star when gas pressure outwards from fusion equals the force of gravity inwards due to the mass of its fuel. And then at the end of its life, it'll start running out of fuel and it'll expand. So now we're just going to turn that into keywords. Come on, rubber. It's been ever so slow. So if I can't get rid of that, there we go, that's better. So work is done by gravity to compress the dust and gas. Really important sentence that. Temperature and pressure increase, so fusion takes place of its hydrogen, turn it into helium and larger atoms. The star is stable when the force of gravity inwards is equal to the gas pressure outwards. And it's probably that part that people might miss, that you've got to say, why is it a main sequence star? So we've talked about why it stops and what a main sequence star is. And that's that.